Welcome back, everyone. Lesson 4, Part 1. I'm your professor of biomechanical engineering, and today we are diving deep into supervised learning, specifically focusing on classification models. As you know from my previous sessions, the work we do here completely bridges the gap between pure abstract mathematics and applied, life-saving medical technology. So, for today's explainer, I really want you to put your strategic hats on. We aren't just looking at some code on a screen today, we're going to see exactly how these algorithms dictate the physical reality of real-world hardware. Let's get into it.
Here is our roadmap for today. First, the biomechanical startup challenge. Second, nonlinear patterns in structural data. Third, support vector machines and kernels. Fourth, decision trees and KNN. And finally, predicting splint safety outcomes.
All right, Section 1, the biomechanical startup challenge. We are grounding our math in physical reality.
So this right here is the physical reality of what we actually do at my startup. We manufacture custom 3D-printed upper limb splints, and these are specifically designed for children suffering from distal radius fractures. These are resting splints, meaning their entire job is to perfectly immobilize the wrist, but do it in a way that's comfortable and functional. A massive upgrade from those heavy, itchy, traditional plaster casts you're probably used to seeing. Now, to successfully deploy a medical device like this, we're locked into some incredibly strict manufacturing parameters. We use polylactic acid, or PLA, which gives us this fantastic mix of adaptability and comfort. And by leveraging generative design, we basically let the computer optimize the architecture to strip away any unnecessary material. The final result? We get the total weight down to a remarkably light 103 grams. We do this by utilizing a specific mix of square and circular perforations, which maintain the structural integrity while giving the patient much-needed ventilation.
But here's the catch. Kids are incredibly active. You know how it is. So, this ultralight splint has to withstand massive, highly localized forces. We're talking anywhere from 190 newtons up to 289 newtons of force, alongside a rotational torque of 13 newton meters right on the distal radius. These are sheer biomechanical loads generated just by the child's own biceps, brachioradialis muscles, and just everyday playground chaos.
Moving on to Section 2, nonlinear patterns in structural data, and the need for classification.
Okay, I want you to pause right here and really consider this critical question. Over in the lab, we've built up a dataset of 1,500 finite element analysis simulated designs. But how do we mathematically categorize a specific, highly complex generative design as strictly safe or unsafe for a pediatric patient?
Well, the answer lies in the data itself. The structural stress patterns happening inside these porous generative designs are wildly complex. They are highly nonlinear. The criteria for safe and unsafe are completely tangled together. A simple linear regression, basically just drawing a straight line, is going to completely fail to separate them. If we want to guarantee the safety of these medical devices, we absolutely must use classification models capable of capturing nonlinear structural patterns.
Which brings us to Section 3, support vector machines and kernels, maximizing the margin.
Enter the support vector machine, or SVM. Academically speaking, an SVM is an algorithm that hunts for the absolute optimal boundary, what we call an optimal hyperplane, to separate our two classes of splints. But it doesn't just draw an arbitrary line. It specifically maximizes the margin. That's the distance between the absolute hardest to separate data points from each class. We call those edge cases the support vectors. By zeroing in on only the toughest cases, the SVM becomes incredibly robust and avoids overfitting.
Let's actually look at the foundational math for a second. The equation you're seeing, C of x, y, f of x, equals the maximum of 0 and 1 minus y times f of x. This is the mathematical constraint that forces that optimization. It essentially dictates a strict penalty for any data points that cross over into our safety margin. By mathematically enforcing this, we guarantee that the algorithm creates the widest possible buffer between a splint design that will hold and one that's going to fracture.
But what happens when our data points are basically locked in a circle, totally inseparable by a flat plane? Well, we use a truly brilliant mathematical maneuver known as the kernel trick. We take our messy 2D nonlinear stress data and we project it upward into a 3D space using a similarity function. And suddenly, data that was impossibly tangled on a flat piece of paper can just be sliced cleanly right down the middle with a 3D plane. It's a game changer. It gives us a flexible, nonlinear boundary without burning through all our computational power.
All right, Section 4, decision trees and KNN, rules and proximity.
Now, a decision tree operates on a strict divide-and-conquer principle. It iteratively chops up the instance space through a hierarchy of logical branches and nodes. At every single split, the algorithm is trying to lower the Gini impurity, essentially making the data more and more pure until it reaches the endpoints, which we call the leaves. What makes this model so beautiful for engineering is that those leaves represent highly interpretable, concrete safety rules that we can physically verify in the lab.
Then, in stark contrast to the rigid rules of a decision tree, we have k-nearest neighbors, or KNN. This is an instance-based classifier. It literally memorizes our entire training dataset. So when we feed it a brand new, totally untested splint design, KNN classifies it just by checking its local proximity in the feature space to the 1,500 designs it already knows. If the majority of its closest geometrical neighbors are safe, it labels the new design as safe. Simple, but incredibly effective.
Finally, Section 5, predicting splint safety outcomes through active experimentation.
This right here is the true intersection of structural engineering and data science. What you're looking at is a spectacular, color-mapped finite element analysis of our upper limb splint. You can physically see the localized von Mises stresses. This visual is exactly what our classification models are evaluating mathematically. They are predicting precisely how biomechanical force is going to distribute across this generative architecture.
And it all boils down to this specific metric, 2.443. Our models have to definitively predict whether the maximum von Mises stresses on any given design will exceed 2.443 megapascals. Why? Because the second the stress crosses that exact threshold, the PLA polymer yields and the splint fails the patient.
At the exact same time, these models are constantly evaluating microscopic structural displacements. Under extreme pediatric loads, we strictly classify a design as unsafe if it deforms by more than a mere 0.015 millimeters. Let me be clear, the margin for error in medical devices is functionally zero.
And I have to say, I share this final outcome with an immense amount of pride, both academically and as a founder. By strategically deploying support vector machines and decision trees across those 1,500 simulated records, utilizing the exact optimal kernel parameters and node splits we just talked about, we achieved an absolute 100% accuracy rate in predicting structural failure.
So I'm going to leave you with this provocative thought as we wrap up today's explainer. If we can capture the wildly complex, nonlinear realities of physical forces, if we can predict the exact structural failure of a 103-gram polymer lattice with an absolute 100% accuracy rate, what other critical medical devices are out there just waiting to be completely optimized with supervised machine learning? Think about the possibilities. Thank you all for your focus today, and I'll see you in the next lesson.